Thank you very much. And thank you very much, everyone, for coming this afternoon and coming to my talk. I would like to start out by briefly saying a few words about the IEEE Magnetic Society, which allows me this year to travel around and give this talk, or to talk to people about how we do X-ray microscopy on magnetic materials. IEEE is an international organization of engineers, electrical engineers originally. Many physicists and material scientists who worked in magnetism always were very closely linked to IEEE. In particular, it has one subgroup of IEEE is the Magnetic Society, which has 3,000 full members and 300 student members. And the society actually does a lot for its members. Not only do we organize conferences like the Intermag and the MMM and TMRC, and some of the people, the one in the audience that work on magnetism probably have been to an MMM. We also support a lot of students at conference. We have very good summer schools. There is this distinguished lectureship program, which allows people to travel and go around. And we certainly also publish a couple of papers, publish a couple of journals. And as I said, I would like to thank this society for making my travels this year possible. So the title of my talk is, and that's kind of the general title this year for this talk, is Going Small, Fast, and Dilute with Soft X-ray Microscopy, and in particular, how this may allow you to learn something on the gigahertz timescale, possibly going up to 10 gigahertz in speed. Also, since you're doing X-ray microscopy, because of the very short wavelength of X-rays that we're using, we can do microscopy with a nanometer resolution. And we can also be very sensitive to small concentrations of materials. And I will try to touch on a few of these items today in this talk, and maybe cover the sensitivity to small concentrations on short length scales in some of the examples I will be giving. I would also like to thank my collaborators. We developed a X-ray microscope over the last 5 years at SLAC, which is part of Stanford University, and a very big part of this development are students and postdoc in the group of Joe Sturr, and in particular Stefano Bonetti, who used to be a postdoc in our group and who's now a professor at the University of Stockholm, and Rupali Kukreja, who was a graduate student at that time and who's now at UC Davis, and Zhao Chen, who is the current student. We also, these projects are quite involved these days, and you need to have people to work with that actually know very well the sample preparations of the samples that you're studying. So we collaborated with the group at NYU and Andrew Kent regarding spin torque oscillators, etc., and also with groups at Hitachi to make very small spin torque nano oscillators and make small contacts that are needed for the devices that we're studying. Okay, so the motivation behind everything we're doing in our group is essentially we want to look at magnetism on the nanoscale. And so if you think about where the importance of magnetism on the nanoscale is, so if you think like the first hard drive that came out in 1956, you could save 5 megabytes of data. It's about 1 or 2 songs in MP3 songs. That is a ton of solid metal. If you want to get it from A to B, you get it on a plane. And it comes with an operator. So it's certainly not very portable. And today's, I mean, I don't have to tell you, we have iPhones and everything. And everything has become much more compact. Storage densities have gone up quite a bit. And if you ask yourself, what made this possible, this miniaturization? It's not only to make everything smaller, but you also need to then preserve the properties that you want on these small length scales. And the materials that are used in a hard drive like here, they don't just scale down. You just can't make it smaller. Then your properties are lost. So what you need to do then, when you want to keep the properties, you need to design new materials and new devices on the nanoscale. And that often means like complex alloys. It's not just iron or nickel ferromagnetic materials, but it's alloys that consist of iron, nickel, gadolinium, what have you. And also multilayers. For example, a modern read-head in a hard drive consists of a multilayer of an antiferromagnet with a ferromagnet, non-magnet, another ferromagnet. So this interface here, the antiferromagnetic interface, is something that I worked on quite a bit during my PhD thesis. Essentially what you achieve by doing this is that you keep the ferromagnetic direction fixed in one, the ferromagnet layer fixed in one direction as a reference layer. Now you have a very sensitive sensor that actually allows you to read out the information on a hard drive that comes from smaller and smaller bits. Now, by going through these very small dimensions into these very complex systems, it's sometimes not enough anymore to just magnetically characterize your devices or materials on a large scale with macroscopic probes using transport or vibrating sample magnetometry or SQUID. You really want to know what's going on inside these devices on the nanoscale. And that's exactly where X-rays are coming in, because as X-rays, as you probably, as you know, is they penetrate the material, so you can look through a material. You can not only see the surface, like with optical lights, but you can like individually probe the magnetic properties of different layers in such a spin wave structure, and you can do it with nanometer resolution, because X-rays, the wavelength is angstroms to nanometers, so that gives you in principle nanometer resolution. And so that brings me to my personal, very brief history of X-ray microscopy. Everything started in 1895 when Konrad Röntgen first published the first X-ray image, the X-ray, so to speak, X-ray microscopy image of a hand. So this was essentially produced using a regular laboratory X-ray source. And it was quite fascinating, because people for the first time really had a tool that allowed them to look through a material to see what's going on inside and something, which was not available until that time. Now, it took us about 100 years from here to here to take X-rays and X-ray sources and X-ray microscopy to a point where we actually not only see topology or a structure, but really could see a magnetic structure on the nanoscale. So, and this is an image, microscopy image using a photo emission electron microscopy taken in 1995, and it shows magnetic domains on a hard drive. And it took us another almost 6, 7, 8 years to really then take this technique, this approach, from 2 dimensions to 3 dimensions, where we not only were able to identify magnetic domains going from one domain to the other one, like here black and white domains and a third direction which is perpendicular to that, but also get information in the third dimension. So distinguish ferromagnetic domains from antiferromagnetic domains, and also look at the interface between these two. And the reason why this was possible is essentially through the development of new X-ray sources. So going from regular laboratory X-ray bulbs over to synchrotrons, which provide like 10 orders of magnitude more X-ray flux than your regular lab sources. Okay, and so where do we get these synchrotrons from? Where do we get these X-rays from? We get them from a synchrotron. And SLAC hosts one of these synchrotrons. So you can see here a very nice picture of the lab, and particularly the synchrotron. The lab itself is much bigger. It hosts several electron accelerator, particle accelerator, and light sources. There's a linear accelerator you may have heard from that starts back here in the hills and comes down. But this is the synchrotron facility where most of our work is done. SLAC itself, and I just want to give you a brief history of the lab. SLAC itself started out as a dedicated high-energy lab. So what Piv Panofsky, when he came from Berkeley to SLAC in the 60s or 50s, wanted to build accelerators to study particle physics. And since the big advantage of SLAC is it's moderately flat. Stanford campus is huge, so there's plenty of room to build these things compared to Berkeley. And so this is how they started doing this. However, as you maybe know, over the years, accelerators have become bigger and bigger and bigger. They also have become more and more expensive. So nowadays, you need larger facilities, like they're available at CERN, for example. And that led to a situation where, like since the mid-2000s, that we're not doing experimental particle physics anymore at SLAC, but that we're using these accelerators, these electron accelerators, as X-ray sources. And with that, the community has changed quite a bit from mostly high energy physics and particle physics and accelerator physics to a very multidisciplinary group of people. We're doing life sciences, we're doing applied physics, we're doing chemistry, we're doing condensed matter physics, magnetism, and all these things. And so the basic principle behind why you always find X-ray labs and electron accelerator labs next to each other is is given by the synchrotron radiation. And so when people built the first electron accelerators very early in the 40s, they saw that if you now have a high energy electron confined or accelerated on an orbit using a magnet, that it radiates light on the side. And the reason is essentially it's like an antenna. So you have a charge, you're moving it up and down, you're accelerating the charge, and it radiates X-rays, radiate electromagnetic waves. In our case, these electrons are at very high energy, so they're essentially relativistic electrons. And because you have relativistic electrons at very high energies, you're not irradiating radio waves, but you're irradiating visible light or X-rays, and that come out in a very directed cone to the front. So now, a couple of years later, people had the idea, so instead of just having an electron beam running or being deflected by one magnet, why don't we just have lots of magnets in succession, and then just have the electron beam wiggle or undulate through such a structure, and that even gives you much more intensity. And this is essentially how nowadays we produce X-rays. So we have an electron and particle accelerator. We keep X-rays, electrons on a closed orbit, but in every straight section that comes up, we have such an undulator that wiggles the electron beam, and then we have X-rays emitted into the front direction, into the forward direction. So what is very nice about this is not only do you have, so this gives you essentially a source of very broadband X-ray radiation. And not only X-rays, you get down to visible light, but from a few eV up to 10 keV, and you can really pick and choose what energy you want to have. It's also polarized. That means depending on where in the beam you pick up your radiation, it's either linear polarized, it's circular polarized. You can have magnet structures that exclusively make circular polarization. So you have full control over your X-ray radiation that you will then guide to your sample. Well, what's also very nice and very important is that, and this is kind of a relic from old accelerator days, if you think about how electrons are stored in such an accelerator storage ring, they're actually stored in little packages. So it's not a continuous flow of electrons that go around in a synchrotron. It's little packages of 50 picoseconds. In our case, it's 50 picoseconds of electrons and at 2.1 nanoseconds apart. So this really gives you like a stroboscopic X-ray source, and that you can use to do image dynamic motions in your sample with 50 picosecond time resolution in a stroboscopic pump probe manner. The only thing, and that's kind of a technical detail, one thing you always have to make sure if you want to do this, you have to carefully monitor how much X-rays are actually incident on your sample. And because if you think about it now, if you have these electrons going around, these electrons emit X-rays. These electrons also kind of collide with gas that's left, or gas atoms that's left in your vacuum. And so you slowly lose intensity, and every 5 minutes they have to inject a few more electrons into the structure here and recapture the intensity, and then you lose it, and so on and so on. So this is a kind of a 2% variation that you typically observe, and you need to be able to compensate for that. That means you need to have a monitor what we refer to as I0 for normalization purposes. Okay, so just to quickly summarize, very often you will see that former accelerator labs are nowadays actually turned into X-ray labs, and that's just simply because circular storage rings are very well suited to produce X-rays or radiation over a broad range from EUV, VUV, up to very hard X-rays, 10, 20, 30 keV, depending on the electron energy and the geometry of the ring. And we have polarized X-rays, we can choose the energy, and we also have a time structure in there. So now how can we use this to learn something about elemental distributions and chemical distributions in our sample, and how can we do microscopy with this. So in my case, what we are mostly doing is we're using a technique used X-ray absorption. So what happens in that case is that you have X-rays, you illuminate your sample with X-rays, and so then, for example, if you have iron in your sample, and you choose your photon energy to be around 710 eV, what you will see is that when you get just to the right energy, you will excite core level electrons into empty states right here above the Fermi level. So this is the core level, this is the 2p level, and you excite you excite electrons from here all the way up into the first unoccupied states above the Fermi energy. Now, when the energy is too low, this transition cannot appear. If the energy is too high, this transition can also not appear. That means, and this is actually given here by this delta function in Fermi's golden rule. Fermi's golden rule in first order gives you essentially the intensity of this absorption transition. It's given by the overlap of the 2p and the 3D wave function in this case, because we are making an excitation of 2p electrons into 3D empty states. And this excitation only happens if the energy distance difference between these two states matches the X-ray energy, plus a certain uncertainty. But this is exactly what gives you the element specificity, because what turns out is that if you, for example, if you look at iron, cobalt, nickel, these transitions happen at very distinct energies. So iron is around 710, 715, cobalt is around 785, and nickel is around 865. And we can very nicely scan the photon energy, and we have essentially an energy resolution of 0.1 eV. So we can very nicely scan the photon energy and monitor the amount of X-rays that get absorbed in our sample. And by doing so, we can essentially monitor this transition, how likely this transition is. Now, what's very nice about this is that when you look at the shape of these empty states here above the Fermi energy, that actually depends very sensitively on whether on the next neighbor. So whether you have iron, like in a metal, or whether you have iron oxide, like in an iron oxide or nickel oxide, then the density of states here will be very has very strong differences between the metals and the oxides, and that you can observe in changes in the line shape. Meaning, if you go from iron to iron oxide, the oxygen the symmetry of the oxygen orbitals around the iron leads to a splitting, and so then instead of one peak, you have two peaks. Same as for the first absorption resonance for cobalt, that splits, the first peak splits into 4, etc., etc. And these are very typical. They are very easy to distinguish. It's maybe one of the big advantages by using X-ray absorption compared to X-ray photoemission, where sometimes the differences are more subtle between metals and their oxides. This is actually, it's a completely different line shape. And this gives you the chemical sensitivity. So very nicely, that allows you to distinguish between a metal and its oxide. And again, this comes in handy when you want to characterize an interface. Let's say you have an interface of nickel oxide and cobalt, and you want to characterize, once you put these two materials together, is it really still nickel oxide cobalt, or do you start forming mixed oxides there at the interface? And then finally, the polarization, the fact that you can choose the polarization, you can that is generated by your synchrotron, or that you use in your experiment, helps you to identify different magnetic states in your sample. So, for example, we stay with iron because iron is always our guinea pig. Now, when you look at iron, and so this simplified density of state here that does not include spins in iron, because iron is magnetic, you will find that you have a different number of empty space for spin up than you have for spin down, in this case, if it's magnetized. And that's exactly what the magnetization is. You have more electrons of one spin sort than of the other one. Now, the effect that you're using is called X-ray magnetic circular dichroism. What circular dichroism means is that using circular polarized light, you will only excite, or predominantly excite, spin up electrons into spin up states and spin down electrons into spin down states. And by doing so, if you have a regular metal that's paramagnetic, you won't see a difference. But in a ferromagnet, you do see a difference. That means for one X-ray polarization, you see a much stronger absorption than for the other one, like in this case. And then if you reverse the magnetization, you can actually reverse this effect. So what you essentially do here is that you're using these optical selection rules and the fact that you have a very well-defined distribution of spins in your ground states, like 3 spin up and 3 spin down electrons, to test the magnetism of your sample. And again, this is referred to as X-ray magnetic circular dichroism. Now, in principle, we can think about other methods of dichroism. So this here, down here, is the X-ray magnetic circular dichroism we just saw. So this is the fact, if you have a ferromagnetic sample, you make use of the fact if that circular polarized light has a different absorption if you are parallel or antiparallel to the magnetization. You can also use linear polarized light and, for example, test antiferromagnets. For example, so in an antiferromagnet, I don't have the spin imbalance between up and down, but I have a spin axis along one direction or the other direction. Now, if I use linear polarization, I will see a different absorption spectrum, whether my linear polarization is perpendicular or parallel to my antiferromagnetic spin axis. And an even more straightforward application of this effect is, for example, let's say you have a polymer. A polymer is really like a one-dimensional chain of something. And so this is a carbon absorption spectrum of a certain polymer. And now if I go with my E vector, my electric field vector, if I go parallel or perpendicular to that polymer chain, I see a very different absorption spectrum depending on which orbitals are available or empty states are available. And this is also something, if you think about 2D materials always show such an imbalance whether you have the E vector in the plane of the material or perpendicular to the plane of the material. Now, finally, if you want to do X-ray microscopy with this, now you have to keep in mind that you're using X-rays. So, and the reason why I'm mentioning this is because in an optical microscope, you have lenses and everything, and you know how to manipulate an optical beam. In X-rays, it's a little bit more tricky. And without going too much into detail, instead of regular lenses, we are using Fresnel zone plates, which is essentially like an alternating array of circles that are either black or transparent. And so it's a diffractive optic where you then generate a focus at a certain distance. So this distance is a couple of millimeters from your sample. And this is exactly the kind of microscopes that we are using. So we have one of these Fresnel zone plates. We have monochromatic X-rays. We make a focus somewhere here. And then we scan our sample through that focus. And like in an STM, for example, but instead of detecting a current or whatever, we just have a photodiode in the back so that we can measure how many X-rays are actually getting transmitted through the sample. And depending on what kind of detector you're using, when you're using like a regular photodiode, you typically don't get any time resolution. But if you use a very fast photodiode, like an avalanche photodiode, then you can actually detect really how every pulse from the synchrotron goes there, and you can then do all these time-resolved measurements. So this is actually a very simple form of microscopy. The microscope in the middle, I will not talk too much about it, but this is essentially like an optical microscope. Now you have 2 lenses, and you have a CCD camera in the back, but you do have Fresnel zone plates instead of using regular lenses. A third way of doing this is using a P microscope, as in the first image I showed you earlier on. There you do not look at X-rays going through the sample, but you're looking at electrons emitted from the sample proportional to how many X-rays get absorbed. So it's kind of an inverse effect there. So you shine X-rays on your sample, the X-rays get absorbed, they emit photoelectrons, and you emit this, you image this lateral distribution of photoelectrons, and you use a screen in the backside. What all of these systems have in common is that you can typically get something like 20, 30 nanometer resolution. And you can use all these effects that I described earlier, like the chemical sensitivity, like the magnetic sensitivity, to get contrast, to see something. Okay, so after this introduction, I would like to give you 3 examples. So essentially, these are 2 examples with a little follow-up. And these examples are really like serving the purpose to show you a little bit how you can use these effects on these length scales to learn something, to answer a question about a system that you couldn't answer otherwise. So one mystery that we started working on a couple of years ago is to look at lanthanum-strontium manganese oxide, which had always showed two different transitions. And what I mean by this, I will explain in a second. So LSMO is essentially one of the guinea pigs of angular resolved photoemission spectroscopy. It has been studied very, very extensively. And the layered material, so it comes in two versions as a bilayered material like this, or like a regular cubic material where you don't have these layering in the crystal structure. The bilayered material shows a metal to insulator transition. And this is always something very fascinating that fascinates experimentalists and theorists in both very much. And around 120 K, so this material changes from a metal to an insulator. And it also changes from a ferromagnet to a paramagnet at the same transition. And that's what people observed at first. But if you now look a little bit more closely, people actually found in many, many different examples and many, many different ways of sample preparation that there's actually a second transition. So where you have the first transition at 120 Kelvin, so this is a magnetic measurement, so this is the ferromagnetic state, and then at 120 Kelvin, the ferromagnetism goes away, but it doesn't go completely away. It's just a little bit stays there, and it slowly goes away at room temperature. So this is from a magnetism point of view. So from an electronic point of view, then much later people also found that even the metal to insulator transition happens, the full metal to insulator transition happens much later. While most of it is gone at 120 Kelvin, if you now just monitor the photo emission intensity from the Fermi edge, which essentially gives you how many electrons are at the Fermi energy, that tells you whether it's still a metal or an insulator. So people found that also this only fully disappears at around 300 Kelvin. So apparently, although this material is supposed to do both of these transitions at 120 Kelvin, they keep a certain portion of this property all the way to 300 Kelvin. The transport essentially gives very similar to this.
I mean, is it metallic and then it goes up, or I mean, above 300 is probably metallic, right? It's going down temperature resistivity.
No, I think it's actually metal down. It's an insulator at high temperature.
Oh, really?
Yeah, it goes from a metal to an insulator. Okay. It goes the other way around, actually. So our first question was, what happens to the magnetism? So we stuck our samples into the photoemission electron microscope and looked at the magnetic domain structure. And so at 115 Kelvin, which is still below that temperature, we see nice magnetic domains. So the black areas is where the magnetization is pointing up. The white areas where the magnetization is pointing down, and the gray areas are kind of there, left or right. Because that's actually the direction we cannot distinguish between it's left or right. It gives us the same contrast. So then we started warming up our sample, and we found that at 121 Kelvin, which is right above this transition temperature, most of this contrast is gone, which means most likely that most of the magnetism is gone, except for these very small inclusions, these very small little areas that still show ferromagnetic contrast. And this contrast only vanishes above 300 Kelvin. And we had different samples. We had this sample. We had from different growers. And we asked them to make these samples for us, because you never know what the sample preparation may affect this. And we found the same behavior on all different samples in different extent. So that's for the magnetism. Now, as I mentioned early on, LSMO comes in two variants. It comes in this bilayered structure, essentially, which shows this transition. It also comes in a cubic structure. The cubic is just a ferromagnetic metal all the way through. with a much higher ordering temperature. So, and as I mentioned, if you have a two-dimensional structure, you will always see a linear dichroism because now your optical properties, whether you have the electric field vector in the plane or perpendicular to the plane, are different. So you will see a linear dichroism. And that's actually what we see from the background here. So if we just go to the oxygen absorption edge and we take an oxygen absorption spectrum, then we actually see whether we have the electric field vector in the plane or perpendicular to the plane. We see a very strong difference here in this absorption feature. And that's very well known for LSMO, that it does have this linear dichroism right here. However, if we go into these little areas here that show the magnetic dichroism, this linear dichroism feature is gone. Which, yeah?
In this phase, the high temperature magnetic field is an insulator or a metal?
The high temperature is an insulator.
This also goes from a magnetic metal to an insulator.
Oh, you mean in the 3D phase? Oh, I don't know, actually, I have to admit. Oh, that I would guess it's still a metal, but it's still a metal probably. To be honest, I don't know the answer. So, but what we learned from this is the fact that everything that is losing its ferromagnetic character at 120 Kelvin shows the linear dichroism. So it shows the same behavior, the same signature, like the bilayered LSMO. And everything that keeps it doesn't show this layered behavior. So it's more like a stacking fault, like the stacking fault that was introduced during growth. So it shows a much more three-dimensional character because it doesn't show any linear dichroism. And while this was always kind of suspected, this actually shows this very nicely that we can show it not only from a structural point of view, but also from an electronic structure point of view, that this is exactly what happens in these samples, that you have inclusions that are not layered anymore. And what's actually very nice to see is that these inclusions are not just isolated and separated magnetically from the rest of the material. So if you for example, in this case, we started at a certain temperature above the ordering temperature, and we just started cooling down. And so we have this little inclusion here that is ferromagnetic. And then while we cool it down, the rest around it becomes ferromagnetic. And this little inclusion just turns from white, and all the area around it turns black because there's a magnetic domain forming that has probably a magnetization pointing in one way, and it just couples to this little inclusion, so it just turns it black as well. So it's actually very nice. So these little things, they're not completely isolated from the rest of the material. They're magnetically exchange coupled to the matrix, but they do have a different crystallographic structure. And I want to skip this one and just come back to the summary of this part, is that this is actually a very nice example how you can, when you have X-rays, and you can choose the energy, so you can go, in this case, from manganese to oxygen. Manganese, XMCD shows you the ferromagnetism, oxygen, linear dichroism shows you the structure. That you can then learn something about imperfections in your sample on this length scale, which in this case is rather large, it's like half a micron. And that you learn something about why your macroscopic measurements of your sample, what the microscopic origin is for the macroscopic measurements of your sample. And so what we actually learned that these stacking faults, or that the second transition is due to stacking faults that are structurally really more 3D-like, and that these stacking faults actually behave more metallic than the host itself. Also, one image that I always like to show in this context is now, since we can do XMCD on the manganese and we can XMCD on the oxygen, and you actually see the same domain structure. Now this is actually at 25 Kelvin, so far below the ordering temperature. And you see the same magnetic domain pattern in both of these, which actually, if you think about how manganese oxide or LSMO, the magnetism comes about, it comes through exchange of two manganese sides across an oxygen side, and that actually leaves a magnetic moment on the oxygen side. And so it's not only the manganese, the 3D metal, which you would believe is magnetic, but it's also the oxygen that carries a magnetic moment in this context. Okay, so that brings me to the second part of my talk, where I want to go a little bit into how we image with very high sensitivity and also give our image to measure dynamics. And so in this one project in our group, when I first joined in '99, there was always something we wanted to do is to measure spin accumulation at interfaces. And so '99, that was about the time when giant magnetoresistance and things became prominent. So in giant magnetoresistance, what this means is that if you have a structure where you run a current from one ferromagnet to another ferromagnet through a non-magnet, then actually the resistance depends very strongly on whether these two ferromagnetic layers are parallel or antiparallel. And again, this is since you can have huge variations, you have to 30–50% in resistance, and these are actually then these devices are used in sensors to detect, for example, the stray field that comes from a bit in your hard drive. So this is essentially the reason why nowadays we have terabyte hard drives and not 40 megabyte hard drives anymore. And the giant magnetoresistance itself was discovered in the mid to late 90s by Albert Fert and Peter Grünberg, who's received the Nobel Prize for this in the mid to early 2000s. Now, this effect has been studied very intensively by engineers trying to figure out what kind of combinations of ferromagnets and non-magnets one can use. However, the physics was always a little bit behind it because there were very few tools to really observe how a spin polarized current goes from one ferromagnet to the other. What I mean by this is, so if you run a current here from one material through the ferromagnet, what happens in the ferromagnets, only you have, for example, you have spin up and spin down electrons in your current that's going in. Only spin up, or mostly spin up spins will make it through the one ferromagnet into the copper. The others will be actually rejected. And then some of these spins will make it through the copper, and then it depends on how many spins really make it to the other layer, what then the exact resistance is. So to be able to understand this a little bit better, what you really want to see is you want to see how a spin polarized current is transported from the ferromagnet into the non-magnet, and how the magnetization in the non-magnet actually changes, or how much magnetization gets induced into the non-magnet. The problem here is that it's a very small magnetization. We always thought it's certainly much less than 10 to the minus 3 Bohr magneton per copper. As a comparison, a regular metal has 1 Bohr magneton. So it's about at least 1,000 times smaller than any regular magnetization. So the first thing that we wanted to do is, even without current, just see what happens if I put a non-magnet next to a ferromagnet. Does this have any effect on the magnetism of the non-magnet? So we had several samples, and I want to show an example of one sample where we essentially just have a 30 to 40 nanometer of a cobalt copper, either a multilayer or an alloy. And so where the copper and the cobalt is either next to each other by alloying or next to each other by layering. And so we put this on a silicon nitride membrane so that X-rays can pass through, and we have a photodiode on the back. And then we put all of this in a magnetic field, and we measure X-ray absorption either with a magnetization in one direction or in the other direction. And again, the difference between these two is then the XMCD effect, which tells us something about the magnetization on each element. And what we could see is actually that, certainly in a structure like this, you would expect that the cobalt is ferromagnetic. It is a ferromagnet after all. But it turns out that we also pick up an XMCD signal from the copper. So this is between 930 and 970 eV. So this is the X-ray absorption spectrum, the blue line of copper with L3 and L2. And this is the difference, the red is the XMCD spectrum between the two magnetizations. And there's a very clear difference. It's about 1% difference in between the two spectra, which points up in one direction for the L3, it points down for the L2. And that's exactly the nature or the structure or the signature of an XMCD effect. And we can estimate that only the static magnetization is probably about 1/10 of a Bohr magneton. And that's just induced by being in contact with each other. And actually it doesn't matter whether you have a multilayered, an alloyed sample or a multilayered sample, we see this XMCD in both cases. They're just meaning by bringing non-magnetic copper next to magnetic cobalt, you will see an XMCD, so you will have a ferromagnetic polarization, spin polarization in these copper, across these copper atoms, and you can see them. 2p to 3d, yes. Yeah, so that's the spin polarization in the copper 3D. Which essentially comes from hybridization with the cobalt. Okay, so, but these were extended films. I mean, it was like silicon substrate and 5 by 5 millimeter films. So then we took our films and we asked our colleagues at Hitachi to pattern them. And so what they did is essentially these films were grown on silicon, and so they they milled most of the film away and just let a very small pillar leaving, and then put nano contacts around so that you can essentially run a current from one contact through the entire structure. In this case, it's a cobalt copper bilayer. Through this cobalt copper bilayer, and then extract the current through the top contact. And so why do we choose this? So the cobalt palladium actually has a magnetization that's pointing in this direction. Our X-rays coming from the other side and are probing the magnetization now. So you run the current from one system to the other. And in this, what happens is that you produce a spin polarized current in here, and then the spin polarized current enters the copper and makes the copper magnetic. And so we are doing this, so we are monitoring now the X-ray transmission through this layer, once with the current on, with the current off, and we compare these two constantly, and that allows us essentially, like in a lock-in technique, to see how the transmission in the copper changes. And so these changes are very small, and that's why we do this kind of lock-in technique. We're really for 700 nanoseconds, we apply the current, then we remove the current, we apply the current, we remove the current. 700 nanoseconds is exactly how one turn of the synchrotron takes. So, and what happens then is if you now monitor the X-ray transmission through that pillar, now this is again the pillar looked at it from the top, and the diameters are 250 nanometers. So we run a current through this pillar, and once, if we run a plus 5 milliamps and we look with a plus circular polarization, we see that the transmission goes up. And if we switch the polarization of the X-rays, we see that the transmission goes down. And this behavior reverses the sign if we change the polarization, change the direction of the current. And again, this is what we refer to as XMCD, so something that changes its sign either with magnetization or with circular polarization. And so what this exactly means is that we have a magnetic change in the copper absorption right here, induced by the spin polarization in the copper. And it turns out it was much smaller than we initially expected. It's about only 3 times 10 to the minus 5. So it's a much smaller injection of spins from the cobalt into the copper than we expected previously. And what's interesting to see is now if we do this for different photon energies, and again, this gray curve here is the copper L3 that we've seen previously. If we do this for certain photon energies and measure how much this absorption changes, we find that actually there's not just one peak, there are 2 peaks. The second peak is exactly the peak that we've seen previously. It's kind of the static magnetization at the interface that changes. And this one here we attribute to the spin polarized current, because it sits right here on the inflection point of the copper absorption spectrum where the Fermi edge is. So this is where the current flows from one element to the other. And what that means is essentially that we have 2 changes in the material. We have the static magnetization right at the interface that changes by the spin polarized current. And then once the spin polarized current makes it past the interface, it then can make it into the bulk and kind of disperse itself into the bulk. So one way to think about it is a little bit, and that's a simplified picture, is essentially, so you have the magnetization in the cobalt, and then once you run and then you have some interface magnetization that it's kind of ordered, but not 100% ordered, because it's kind of between the 2 materials, between the cobalt and the copper. Once you run the current, you fully magnetize the interface, and you then partially also, you change the interface, you change the magnetization interface, And then that you already lose a lot of your spin polarization right there. Because this essentially by spin torque exchange, you pull the magnetization at the interface into the same direction as the cobalt. And then the rest of the magnetization of the spin polarization then travels into the bulk and induces this very small moment in the bulk. So what's interesting about this is because, again, if people knew from experience that for many, many years that you never achieved the spin injection efficiencies that you would hope from theory, and it was always about like 30%, 50%, something like this. And I think this really showed us why this efficiency is limited, because you have a magnetization at the interface, which when you run the current through it, you lose already most or half of your spin polarization yet you generate in the ferromagnet, and you use this by magnetizing this interface, or by remagnetizing this interface. Okay, so and that brings me to my last example, and that is a short example actually. Now we have the spin polarized current that runs from a non-magnet into the ferromagnet, and in some cases what you can do with this when you have a very in our case both the non-magnet and the ferromagnet were patterned into nano contacts. Now what you can also do is you can have an extended ferromagnetic layer on the top, and what people do is with that they use it to induce dynamics in the ferromagnet. And so in principle one distinguishes between two different cases, and one case is where you have a spin polarized current running, the blue layer here produces the spin polarized current, and then you separate it from a ferromagnet with a small non-magnetic layer, and then you inject it into the ferromagnet, into the second ferromagnetic layer. Now you induce dynamics here, because so what happens is you have the spin polarized current, and they're not 100% aligned, they're a little bit misaligned, and by doing so you kind of like start to wiggle them a little bit, and these wiggling motions now can excite collective motions of the whole thing, and these can have different shapes. So you can have a very localized excitation, like in this case here, where you just at the position of the contact excite the ferromagnet, and you really have like a bullet or a spin soliton that you excite here. Or you can have the situation where in a geometry like this, where you get like spin waves excited from this contact position, and it's pretty much like throwing a rock into water. So essentially we're distinguish between localized excitations and propagating excitations. But just to make the point again, I mean, these are I want to say very simple, but these are the model cases essentially that you can calculate on a piece of paper. They kind of, they're only looking at the very fundamental interactions in these systems, but not the real geometry and the real structure. So we looked at such a system, and so here, this is now a 1x1 micrometer area that we looked at in our sample. There's a nano contact. So, and just to simplify or to explain this, there's a current now coming or running from the bottom layer through this nano contact, and then this current kind of disperses into the extended ferromagnetic film. And so this is where the spin polarized current is injected. And we were always thinking, if you do something like this, we had a geometry where everything should be localized to the area where the nano contact is. However, we found something very interesting. So now, in this case, we took images using this troposcopic method, and this is essentially a 160 picosecond video. So the entire movie is 160 picosecond, and then it circles around, and as you can see, it's periodic. It comes always back to the original point. And what you see is everywhere where it's blue, the magnetization is actually going into the plane, and where it's red, it's coming out of the plane. And what's interesting is that it's actually not just localized to the point of the excitation, but it's actually kind of like almost like emitting in one direction. You can essentially think about like one wavelength of a spin wave going into this direction. And it's going around and around and around. And so we were wondering ourselves, why is this the case? Why do we have this very peculiar behavior there? And the reason is that if you would model this, you would just look at the magnetization here, maybe at the external field and the field that's generated by the spin-injected current. It turns out that the real field distribution is much more complicated. Now, and so there are two ways of showing this. And so this is one way. So the small little red arrows are given by the external field. So that's the 700 Ørsted that we apply externally. And then also you have the spin polarizing contact down there, which is essentially like a little nanomagnet which sits underneath that film. It's like a simple dipole magnet. So this produces a field that goes like this, or in this case like this. So it comes out of the plane here and goes into the plane here. So this makes a stray field. So we have the dipolar field from the polarizing layer, we have the external field, and you also have the Ørsted field, meaning if you run a current through here, then right-hand rule applies, so you get an Ørsted field that goes essentially around the nanocontact. Now you add these three fields and you get a kind of a very complicated field distribution around the nanocontact, and that leads to if you think about it, you can also plot this in terms of ferromagnetic resonance frequency. That means the ferromagnetic resonance frequency is given by the effective local field at every point. So naively, one would expect that it is kind of homogeneous where the nanocontact is, but it turns out it isn't. It's very inhomogeneous, and it actually goes much higher than the background on the top and the bottom, and it's lowered on this side, and it's actually lowered preferentially into one direction. And that's exactly what we see if we know, if we go back, that's exactly what we see, that this would be the direction in which the ferromagnetic resonance frequency is lowered. So there's kind of a potential valley where a magnetic energy can escape, a spin wave can escape, and that's exactly what we see. That's kind of nice to think about it. So now you can think about, how can I shape my contact, how can I shape the fields around the contact to just emit a spin wave in one direction, and maybe do this even more efficiently. Like in our case, it's really just one wavelength. You would actually hope that this goes maybe much further, like 200, 300, 400 nanometers or something like this. And then you could have an emitter here, and you could have a receiver here, and that would also allow you then to transmit information using spin wave energy, which is potentially much more efficient than using electrical currents. Okay, good. So and that brings me to my summary. What I wanted to show you is a little bit, give you an introduction into X-ray microscopy and what you can do with it. In particular, using soft X-rays at a synchrotron. Meaning, what soft X-rays give you is not only just high spatial resolution, but it gives you the ability to really distinguish between different elements in your sample and learn something about the contributions in the energy contributions that really matter on that length scale, which is otherwise very difficult to evaluate just from theory or from a macroscopic measurement. And so I showed you a little bit about the LSMO, where we looked at defects. I showed you a little bit about how to measure spin injection from a ferromagnet into a non-magnet, and how this spin injection then is used or applied in a spin torque nano oscillator to generate spin waves. And everything I've told you so far, except maybe the latest experiments, can be found in this wonderful book that was written over a couple of years in our group by my former advisor and boss, Joe Sturr, and Hans-Christoph Siegmann, who used to be at the ETH in Zurich, and then came to join our group as a post-prof. Since in Europe you have to retire at 65, and that's sometimes people don't like that, so they come over here and they continue to work. And thank you very much. So the question was that the spin accumulation that we found was much smaller than the one that we actually suspected before the 10 to the minus 3. The 10 to the minus 3 was also like an experimental limit. So people have tried with other methods to see whether they could see any evidence of spin accumulation in the non-magnetic layer, and that's pretty much their upper limit that they extracted, because they kind of figured out what their error bars in their experiment is. Although, yes, I think in general GMR theory, you would expect something of the order of 10 to the minus 3 to 10 to the minus 4.
Right, so if the spin current is much less, why is there so much GMR?
That's a good question, yes. I think there's no answer to that. There's a new mystery, so to speak, yeah. Oh, so the way you do this is actually, you don't change the X-ray energy in the synchrotron. That would be very difficult. So the electron energy in the synchrotron is fixed. But so what you can do is you can typically, there are two ways to generate them, to generate X-rays. One is at the edges, where you bend the electron beam around. And actually, these are broadband sources. So there, where you do this, you have an emission spectrum from the visible to a certain upper energy. The other thing is when you look at where you, but you don't tune the electron energy of the electrons. That is given by the geometry of the ring. It's actually very difficult to do this. But if you use these undulating sources, there you can actually change the magnetic field. So what they do is, there are two ways of doing this. People have tried to use electromagnetic undulators, where you do, but that's kind of a little bit tricky because the distance between poles in the magnets is only about 40 millimeters, and then getting strong electromagnets is kind of tricky. So they do this actually with permanent magnets, and they just change the distance between the permanent magnets. And by changing the field, you change the emission characteristics of that undulator. No, so the question is whether the circular X-rays can detect the direction in antiferromagnets. So, what? Sorry? Oh, yeah, so what you can do is using linear polarization. This is when you can image antiferromagnets. And so, let me, yeah, here. So, and that would be, I actually have done a lot of nickel oxide in my life. In our group before I joined, they did a lot of lanthanum iron oxide. Lanthanum iron oxide is also an antiferromagnet. And so, but then you have to use linear polarization. So essentially, the way to think about it, in dichroism, you always probe any kind of breaking in the symmetry. So if you have a perfectly cubic system, your optical properties do not depend on the polarization of the incoming light. I mean, whatever you do, whether you come like this, you will always see the same. Now, once you change the symmetry and you have like, once you break the symmetry in an antiferromagnet, now suddenly you have a preferred axis given by the spin axis. Then your optical properties will be depending on whether you're parallel or perpendicular to it. And in this case, then the absorption, your absorption line shape changes for the two situations. And this is actually it's the same absorption edge like this, just for iron oxide, and just blown up a little bit.
Do you require particular direction for this no vector? Does it have to be in plane, out of plane?
It doesn't have to be in plane or out of plane. It just has to be, you need to know where it is. So that you at least, if you have a sample that has many magnetic domains, then you wouldn't see anything, because then macroscopically that sample always, that appears again as isotropic. But if you want to, for example, measure antiferromagnetic domains, like, go a little bit back further, like for example, in this case, these are actually domain images of ferromagnetic cobalt on antiferromagnetic nickel oxide. And just the illustrator put it a little bit together. So these are domains where the cobalt would be either pointing up or down, and the antiferromagnet axis is like this. And while here, the cobalt spins point left and right, and the antiferromagnet axis is like this. So you can then correlate antiferromagnet and ferromagnet together.
Is that the spatial resolution? Like in 10 microns, you see about 3 domains. Is that a spatial resolution?
That was the spatial resolution at that time, yes. So that's from 1995. And
What's the best spatial resolution now?
typically,
Domain size of what?
20 nanometers, 10, anywhere between. So in X-ray microscopy, when you do scattering techniques, you can get a little bit lower. But so typically the spatial, I would say 20 nanometer, and then that's a safe number. Under certain conditions and certain samples, you may get a little bit better than that.
So when you do spectroscopy, what kind of spatial resolution can you get?
The spatial resolution in spectroscopy, that depends a little bit. Right now, I would say in the P microscope, like these images were taken probably 100 nanometer, roughly. The Stixum we are currently, in our microscope, it's not as good. It's about 200 nanometers. In other microscopes, it's probably 50. And there are some recent publications on very particular samples where they actually got a spectrum of a 10 nanometer particle. But this is a very special application, and that's a very specialized system. So you probably have to wait another 5 years or so before this becomes standard. But this is actually where ultimately it would be going to 5 to 10 nanometers. The question at this point is really, it becomes an intensity question. I mean, even if you can see a 10 nanometer domain, that doesn't mean that you can get a spectrum from that 10 nanometer domain. It turns out something, if you do X-ray microscopy, you will learn over the years is that your eyes are incredibly sensitive. Your eyes can see domains that no filtering algorithm can ever see or detect. So we have done microscopy very often on this. We look at the screen and say, there are the domains. And then you put a line scan through it, and that line scan is just noise. And I'm just saying this because so that means the optical resolution, so what you can put in a paper and say people, so see there's a structure at 10 nanometers, that just doesn't mean that you can get, that's why I'm saying even these microscopes have a resolution of 20 nanometer, a spectral resolution of about 100 maybe or something like this.
I have a question about you observe the SMCD oxygen in LSM.
Mm-hmm.
So because oxygen only has 2 outputs, the normal SMCD you need transition from 2P to 3D.
Yeah.
I'm thinking about which absorption.
Okay, that's a good question. So the question was why we can see XMCD in the oxygen in this one example that I had here. And you're right. So typically when you do XMCD, very often, at least you're looking at an L absorption resonance, which is so 2P to 3D. The reason is that you actually, to learn, to see something, you actually need the spin-orbit coupling down here as well, which in oxygen you don't, because you go from a K edge, from 1s to 2p. So you don't have this spin-orbit. That means you cannot actually see the spin. You're not sensitive to the magnetic moment of the sample, to the spin. You're only sensitive to the orbital moment. The selection rules still apply because the selection rules actually apply to the orbital moment. They're given by the orbital moment. But you don't have, in case you have heard about, so this technique also allows you via some rules, for example, to distinguish between spin and orbital moment. So you can look at the different spectrum and can actually calculate the spin and orbital moment. And I haven't talked about this and didn't go into detail. So this is something that falls away when you look at oxygen or carbon or whatever, because then you only go from 1s to 2p. But you're still sensitive to the magnetic to the orbital magnetic moment in the oxygen. Then
You can see carbon.
You can see carbon. Yeah.
You can do this in graphene.
So graphene is unfortunately very thin. So we have done a lot of work on a proton irradiated carbon. I work together with a group in Leipzig. They do this a lot, so that they take HOPG and they hit it with protons and induce defects, and then you can pick up the magnetic signal, the ferromagnetic polarization.
I'm just wondering
But graphene is just too thin. It's
I just wonder if they can actually see spin injection. And people have done this device, like
yeah.
where the light times at telemix volume, they expect micron. You never see them.
Yes.
When you do this to actually verify that everything dies, you
We-
20 nanometers.
We have thought about it a lot. The problem really with graphene is that it really gets to a sensitivity question we haven't thought about yet. There are two problems with graphene. First of all, it's just a monolayer, so that makes it difficult. The second problem is most of the experiments I have shown you are either done in vacuum or at least a decent vacuum. So, but if you hit your sample with X-rays, at 10 to the minus 6, you grow about a monolayer of carbon on there per second. Even if you go to 10 to the minus 9, you have like a minute per monolayer. So that is a problem if you want to detect a monolayer of graphene. So, and I think that's something that nobody really has addressed so far, how to deal with.
Monolayer of other elements, because here it's limited by your carbon environment.
Yeah.
Have another, say,
You can do a monolayer of other elements. Just carbon is so difficult because you're immediately when you irradiate with X-rays, you get carbon on carbon. So it's kind of defeating the purpose.
quick question. So the absorption from 2D to 3D, that depends on the density of states at the EF, or it depends on the total number of states above EF?
It depends on essentially. I mean, when you go through the absorption resonance here.
Like here, spin up and spin down, they have different density of states.
Yes.
But in terms of densities, actually the spin up state actually is greater than the spin down state. So the density of states, the spin down is higher.
Yeah. No, so the empty density of states is higher. Oh, yeah. So you see the empty densities of states.
The density of states at the EF, if you look at the
Oh. No, so you're right. So it's maybe that graph is not so good. No, it's the total density of states that you would see that. At EF and above, because I mean you only have like a certain energy resolution, so you're actually integrating always over like. It's a convolution, yeah. I mean typically when you go in there with the energy resolution that you have, you would probably at least get a window from here to here. So I should actually put an energy scale on there that it's easier to explain. That's actually a good point. You need to have an X-ray absorption, yes. So,
in case of this kind of quantum edge state, you have spin polarized electron. You see that electron?
so these, I mean, to see the spin polarized, you need to have a spin polarization in the states that you're looking at. For example, in the copper, that was a little, for example, in the copper, that's a little tricky because the spin polarization that you excite is actually in the S states. But so since there's a strong hybridization between S and D, you actually can't see this. But let's say you have a spin polarization in the S states, but you excite into the D states, you will not see that spin polarization. Does this answer your question?
I think that's what, but I mean, like, for example, in two-diode system,
Uh-huh.
in the quantum power regime, you can have a kind of odd number of nanometer which has spin polarized current flowing at the edge.
Uh-huh.
And like using this kind of technique, because those electrons simply like electron gas doesn't associate with any orbitals.
Oh. I would.
Yeah, so I'm just curious.
It sounds like the answer is no if they are. But I would have to think about this. It's definitely not straightforward. I mean, they have to be in some defined orbital so that you know. You would probably pick something up, but then if they're not interacting with any of the orbitals that or bands that you're probing, then you probably have no chance of seeing them. That's true.
Are there scattered
That's actually, I'm not too familiar with that. People do X-ray photon correlation spectroscopy to look at, you're thinking about time scales or spatial, you're thinking about temporal or spatial correlation? Oh, so yes, so yes and no. There are ways of, good question. There are people who actually calculate absorption spectra that try to get these correlations out. So I should maybe say a very popular way of trying to model X-ray absorption spectra is using multiplet theory, where you essentially you take your atomic orbitals and then you're trying to put them into particular symmetry so that you know how much every orbital contribute at in what linear combination to your absorption spectrum. And there are usually, I think, parameters that you can choose that mimic correlations. But this gives you kind of a very empirical picture, kind of more like knobs that you can turn. But I think in general, this is something that is not, you don't get a deeper understanding of any kind of correlations.
I think we interrupt the discussion, but we're running out of time. So let us thank our speaker again.
Thank you.